Hi, today I'll show you how professional power inverters work. For this project, the power inverter has output voltage regulation, overcurrent and short circuit protection, and reverse voltage polarity protection. The block diagram of such a power inverter looks as shown. It takes in low voltage DC of about 12 volts and gives out a modified sine wave AC of 220 volts. A modified sine wave inverter is more simpler to make than a pure sine wave inverter. The low voltage DC is fed to a DC step-up converter or switch mode power supply and is converted to high voltage DC of about 320 volts. This high voltage DC is then fed to a H bridge, which basically switches the high voltage DC back and forth to simulate alternating current. The H bridge is controlled by a suitable driver circuitry. The first section is the DC converter switch mode power supply, and this converts 12 to 320 volts DC. Before you look at this section, let's have a look at the input reverse voltage polarity protection circuit. The input reverse polarity protection circuit looks as shown. It's based on an N-channel power MOSFET. When you connect the battery in the right manner with the positive being on the upper rail, the gate of the MOSFET will be pulled to about 12 volts, allowing it to conduct and so current to flow through to the rest of the circuit and back to the negative of the battery through the MOSFET. When you reverse the connections of the battery, the gate will be pulled to minus 12 volts respective to the source, keeping the MOSFET from turning on. This will block current flow from the battery to the rest of the circuit because the MOSFET will be off. Back to the DC to DC converter. It's built on the SG3525 IC. It has 16 pins and all the connections are as shown. Pin 1 and 2 are the inputs of the air amplifier. Pull pin 2 to 2.5 volts generated by the defender network made up of R3 and R4. Pin 16 generates a reference voltage of 5 volts. Leave pin 3 and 4 unconnected because they are not needed. The operating frequency is set by the timing capacitor C1, the timing resistor R1, and the daytime control resistor R2. C1 is 1 nanofarad, R1 is 10 kilo ohms, and the daytime control is 47 ohms. With these values, the frequency is set to about 70,000 Hz. Connect pin 8 to ground through a small capacitor to ensure that there is soft start capability. Connect pin 9 to ground through a small capacitor of 10 nanofarads and to the inverting input pin 1 by a capacitor and resistor network as shown for compensation. Pin 10 is the shutdown pin and it controls whether the outputs of the IC are enabled or disabled. Pull it down to ground through 10 kilo ohms resistor to enable the outputs. When it's pulled up to a logic voltage, the outputs are instantly disabled. The outputs are available at the output pins 11 and 14 as shown. Pin 12 is the logic and power ground of the IC. Pin 13 is the voltage supply to the output drivers of the IC. Pull it up to VCC. Pin 15, which is connected to a VCC voltage of about 12 volts. The IC works as a push-pull driver, meaning that you have pulsating DC at pin 11 and 14 and the output signals will be complements of each other. When you have a high signal at pin 11, pin 14 will be low and vice versa. The IC cannot supply much current and this is not ideal for operating MOSFETs at such high frequencies. So a current boost network is needed. I've made such a simple network using the bipolar transistors, the NPN BD139 and the PNP BD140 configured as shown. This acts as a voltage follower, but they will boost the output current to more than 1 ampere. Let's say on the first case you have a high output at pin 11 and a low output at pin 14. Q4 will turn on and pull down the gate of the MOSFET Q1 to ground, forcing it to remain off. Q3 remains off because it's NPN. Q5 now turns on because its base is pulled up to about VCC, but Q6 remains off. The gate of the MOSFET Q2 is pulled up to a voltage almost equal to VCC, ensuring that it turns on quickly. Now you have a current path flow from 12 volts through the lower side of the primary winding, through the MOSFET Q2, through the shunt current sensing resistor R10 and to ground as shown. On the next stage, pin 11 goes low and pin 14 is held high. Now Q6 turns on and Q5 turns off. The MOSFET Q2 will turn off quickly because the transistor Q6 will pull down its gate to ground. Now Q4 turns off, but Q3 will conduct and pull up the gate of the MOSFET Q1 to VCC, forcing it to conduct quickly. Now you have a current path flow from VCC through the upper half of the primary winding through the shunt resistor R10 and to ground as shown. This makes one oscillation and the process repeats over and over 70,000 times per second. The shunt resistor R10 is for sensing current. It's about 1.5 milliohms. As more current flows through, there will be a voltage drop across here, and this will be fed to the current sense circuit, which protects the circuit from overcurrent and short circuit by providing feedback to the IC. I'll show you that in a moment. For the transistors, they are the IRF2804. These are high current power transistors and they can handle more than 200 amperes without a problem, and the on-drain source resistance is about 3 milliohms, so they are good for this project. C6 is a filtering capacitor connected close to the center tap of the transformer. It's about 3300 microfarads and at 325 volts. Use the largest value capacitor you can find. For the transformer, it's a ferrite power transformer so that it can handle the high frequency. The primary turns are 1.5 on each half or 3 in total with a center tap in between. The high voltage secondary is about 45 turns and each of the 3 auxiliary windings is about 2 turns each. The high voltage output is fed to a high frequency bridge rectifier, diodes D4 through to D7. This will rectify this to DC, which is filtered by the capacitor C10 and C11. C10 is rated for at least 400 volts and so is C11. C10 is at least 100 microfarads and C11 is 100 nanofarads, non-polarized capacitor. You also need a small minimum load. The resistance is to 70 kilo ohms and it's at least 3 watts. Notice the ground references. You have the low voltage ground. You have ground 1, which is the ground reference for the high voltage DC, which is also the ground reference for the first auxiliary VCC voltage. You also have ground 2 and ground 3, which are ground references for the other 2 auxiliary VCC voltages. For output voltage regulation, a simple circuit made up of the Zener diodes and the optocopper is as shown. The Zener diodes are rated for 110, 110 and 100 volts. When 320 volts is exceeded on the output, the diodes conduct and create a current path flow through the internal LED of the optocopper and to ground via the resistor R11, which limits the current. The internal transistor of the optocopper will conduct and create a current path flow from 5 volts VCC through to the voltage feedback pin, which is the inverting input pin 1 of the IC. And when this happens, the output duty cycle is reduced, ensuring the output voltage does not increase further. For the 5 volts VCC, a simple linear regulator to step down 12 volts from the battery to 5 volts is as shown. The next section is the MOSFET H-bridge, but before you look at this, let's have a look at the H-bridge driver control circuit. The MOSFET H-bridge control circuit is as shown. It's also built around the SG3525. Connect everything as shown. The amplifier is completely disabled. The frequency is set to somewhere between 50 and 60 Hz. Change the timing capacitor to 100 nanofarads, and the timing resistor is made up of the 100 kilo ohms resistor at 29 and potentiometer of 50 kilo ohms. The potentiometer allows you to alter the frequency from about 47 to 70 Hz so that you can carefully select a frequency of 50 or 60 Hz. The daytime control resistor is 100 ohms. You can use any value from about 22 to 100 ohms as desired. You'll have 2 output signals at pin 11 and pin 14 as shown, signal A and signal B, with a small daytime in between the output passes. The MOSFET H-bridge circuit is as shown. You need 4 MOSFETs. The IRF-P460 should work well. They are rated for 20 amperes and a drain source voltage rating of 500 volts. To control the MOSFET, you need 4 optocouples which provide isolated gate drive for each of the MOSFETs. The drive signals are fed at driver A input and driver B input as shown. Let's say in the first case you have a high signal at driver A and a low signal at driver B. The transistor Q12 turns on and pulls down the cathode of the optocouples U3 and U5 as shown, allowing the internal LEDs to turn on, and so does the internal transistors. The optocouples U6 and U4 will be off and so will be the MOSFET Q8 and Q10 as shown. When U3 turns on, now you have a current path flow from VCC2 of 15 volts through the internal transistor and to the gate of the MOSFET Q7 through the gate resistor 19 as shown. This causes Q7 to turn on. Q9 also turns on because its gate is pulled up to VCC1 reference of 15 volts. Now you have a current path flow from the high voltage DC 320 volts through the MOSFET Q7 through the load through Q9 and to ground 1 reference as shown. So you have a positive here and a negative here across the road. On the next stage, driver A goes low or is fed by a low signal, but driver B is fed by a high signal. The transistor Q12 turns off and so does the optocouplers U3 and U5. The MOSFETs Q9 and Q7 also turn off, but now the optocouplers U6 and U4 turns on, and so does the MOSFET Q8 and Q10 because their gates are pulled up to VCC reference of 15 volts VCC1 and 15 volts VCC3 respectively as shown. Now you have a current path flow from high voltage DC through the MOSFET Q10 through the load with a positive here and a negative here through the MOSFET Q8 and to ground 1 reference as shown. And this makes one oscillation and the process repeats at about 50 times per second. Notice the ground references for the upper MOSFETs. The raw MOSFETs are both referenced to ground 1, but the upper left side MOSFET source is referenced to ground 2 and its gate is referenced to VCC2. The upper right hand side MOSFET is referenced to VCC3 and its source is referenced to ground 3 as shown. All the gate source discharge resistors are written for at least a quarter watts and they are 10 kilo ohms each. The gate resistors are 470 ohms and at least half a watt each. The optocouplers are also the PC817. The voltage waveform across the road will be something like this, and it will be swinging between plus 320 volts and minus 320 volts. The load is fed by an alternating current as shown. Also connect two resistors to ground 1 reference across the load. These can act as spike arresters in case there are any spikes generated across the primary winding, such as in a case when you have an inductive load. The 12 volts power supply to the anodes of the optocouplers is just the 12 volts also being fed to the switch mode power supply low voltage side. The final part is the overcurrent protection. The voltage developed across the shunt resistor at the DC-DC converter is fed to an op-amp. The first operation amplifier basically amplifies the voltage input by a factor of about 22, and the second one is configured as a comparator to switch whenever the output of the first op-amp exceeds 2.5 volts. The gain is set by the resistor R36 47 kilo ohms and R37 2.2 kilo ohms, so the gain is about 22 to 23 times. When the current flowing through the shunt resistor on the primary of the DC-DC converter exceeds about 75 amperes, the voltage drop is amplified such that the first op-amp gives an output of more than 2.5 volts, and because the second op-amp inverting input is set at 2.5 volts by the definer network made up of R39 and R38 as shown, and now you have an input more than 2.5 volts at the non-inverting input, the op-amp will give a high output signal of 5 volts, and this will be fed to the shutdown pin of the IC, and this will instantly disable the outputs, protecting the circuit from an overcurrent case. Also, an LED will be illuminated, indicating that you have an overcurrent situation or short circuit condition. This will continue until the overload is corrected. The operational amplifiers are contained on the same chip of the LM358 IC. The 5V DC is from the linear regulator, the LM7805, discussed on the previous sections. With that being said, I hope you have enjoyed this video and learned something new. If so, make sure to give it a like, subscribe to my channel, share with your friends, check out some of my other videos. Have a nice time and I'll see you in the next video.